So good afternoon, and I'll begin my talk by thanking the organizers for giving me this opportunity. And I'm going to talk about overview of Flavour physics. So we know that standard model is not complete and it has to be extended. We have had so many ideas about the extension of the standard model, like standard model, it cannot accommodate, there are many open issues in the standard model. It cannot accommodate dark matter. It cannot also explain the No, it's okay. So it cannot also accommodate neutrino mass and observe baryon asymmetry of the universe. So it has to be extended. So the question is how to go beyond the standard model, and can Flavour physics help us to give some hints to how to explore beyond the standard model? If we look into the past, then we know that standard model, Flavour physics played an important role for the formulation of the standard model, and can we hope that it will also give us some hint to go beyond the standard model? So the importance of Flavour physics is it encompasses many of the open questions in the standard model. Why there are three generations of quark masses with three generations of quarks with hierarchical masses. What determines the hierarchical structure of the CKM matrix? Although the CKM paradigm, it explains CP evolution so well, but it is not really sufficient to explain the observed baryon asymmetry of the universe, and hopefully we will get some idea beyond the standard model from Flavour sector. So we can search new physics signature either through direct production of new particles at colliders, and we have not seen any new particles at the LHC so far. And the second method, it exploits the presence of virtual states in the decays of standard model particles. And Flavour observables are quite sensitive to these virtual effects. For example, if we see this cartoon, at LHC we can produce new particles up to 7 TeV, whereas if we look into the anomalies in the B sector, like from B to S mu mu, we can probe the new physics scale up to say 30 TeV, and from the muon going to 3e, we can go up to 10 to the power 3 TeV and so on. So the CKM matrix, it plays a central role in the study of Flavour physics, and the unitarity of the CKM matrix is represented by the unitarity triangle. The unitarity triangle, which is relevant for the B sector, is this one, and from the present measurement, we can see that this unitary triangle is precisely measured, and the tip is very stringently constant. However, there is it still allows new physics up to say 10 to 15% in the Flavour changing neutral current processes. There are few open issues or the long-standing issues in the exclusive versus inclusive measurement of the CKM matrix element VUB and VCB. So this is the exclusive measurement of VCB from the decay of B going to D star L nu, and this is the exclusive measurement of VUB from the decay mode B going to pi L nu, and this yellow band, it corresponds to the ratio of VUB versus VCB, and this red region, it is the average of these three measurements. However, this is the inclusive measurement, and it is important to note that the VCB, it has the deviation between the exclusive and inclusive at about 2.6 sigma, whereas for the VUB measurement between the exclusive and inclusive, the discrepancy is around 1.5 sigma. Now, quickly coming over to the mixing of neutral mesons, we know that the neutral mesons K, D, B, and B, S, they mix with each other, and this is how the Flavour states they evolve with time. And these are the physical states, which are mixture of the Flavour states. So the two parameters which are important for the study of the neutral meson mixing is X, which is proportional to the mass difference between the light and heavy state, and Y parameter, which is related to the lifetime differences between these two physical states. So if we consider the decay of a pure B0 meson at time t to a final Flavour state F, CP eigenstate, then the decay rates are not identical for B0 going to F and B0 bar going to F. They are different. And from their difference, we can get the time-dependent rate asymmetry. And this rate asymmetry is described in terms of two parameters. One is direct CP violation parameter. Another one is mixing-induced CP violation parameters. So this is a quick summary of the CP violation in the mixing. So in the first one, this K0 and K0 bar, it is proportional to VTD, VTS more amplitude more square. And for D0, D0 bar mixing, it is proportional to VUB, VBC. For B0, B0 bar, this is VTD, VTS. So the mixing is proportional to the real part of the product of the CKM matrix element, and the CP violation part is proportional to the phase. So for K0, K0 bar mixing, this mixing is proportional to A lambda to the power 5. So CP violation is very small, and also the mixing is small. For D0, D0 bar mixing, the super slow, because this here in the loop, the B quark is flowing, and this is loop suppressed. And this is also, we will also see very small CP violation in D0, D0 bar mixing. For B0, B0 bar mixing, we will have large mixing as well as large CP violation, whereas for BS, BS bar, the mixing is very fast and small CP violation. So coming over to the CP violation and mixing of neutral meson, this is the effective Hamiltonian, which describes delta F equal to two processes. So if we include the new physics parameters, then there will be 5 new 4 fermion operators which can contribute to this effective Hamiltonian. And these are the expression for these 5 parameters. And if we see here the corresponding Wilson coefficient, which can be written in terms of the Flavour variable as well as loop variable, and lambda is the new physics scale, and the corresponding chiral enhance operators, this Q1 tilde bar 1, 2, 3, they are obtained from this Q1, Q2, Q3 by replacing L by R. So if new physics will contribute to the M0 bar mixing at the tree level, then this Flavour factor will be of the order 1 and loop factor will be order 1. And if new physics will contribute at the loop level, then this Flavour factor will be the product of CKM matrix element, and this loop factor will be weak coupling square. So if we consider the new physics at the TeV scale, then the scale that we can probe at LHC is given by this light colors. This green corresponds to the K0, K0 mixing. The yellow, it corresponds to this corresponds to D0, D0 bar mixing, and this one it corresponds to B, and this one it corresponds to BS bar mixing. So if new physics will contribute to the at the loop level, these are the scale that which we can probe the various Wilson coefficient or various couplings, and these are obtained by considering only one operator at a time. So if we'll consider the O1 type of operator, then this is the scale to which we can probe in LHC. And if we can go to HL LHC, then this dark region can also be probed. Similarly, if we can parameterize the new physics amplitude in for B or B0 bar mixing transition amplitude, then this is the how we can parameterize the new physics scale. The standard model corresponds to CBQ equal to 1 and the phase equal to 0. So for B0 B0 bar mixing, this is this green region, it corresponds to the information that we got from LHC, and the blue region, it corresponds to the allowed parameter space for HL LHC. Similarly, for BS bar mixing, the green region, it corresponds to the UT fit result for LHC, and the blue region, it corresponds for HL LHC. So we can see that the standard we can have say or we can rule out the standard model region at more than 1 sigma region for the current information from LHC. However, from HL LHC, again, we can constant the new physics parameters at 1 sigma level. Now coming over to the mixing and CP evaluation in the charm sector. The no mixing point is 0, 0 point, and these are the this is the allowed region in X and Y plane. So the no mixing point in D0, D0 bar mixing is ruled out at 11 sigma point. Similarly, the CP evaluation at this is the region for no CP evaluation. So we can see that CP evaluation can be established at D0, D0 bar measure more than 2 sigma level. Now I'm coming over to CP evaluation in charm decays. CP evaluation in charm decays is expected to be very small as the B quark is flowing in the loop, and that is why the loop contribution is very small. Also in charm decays, the Jim mechanism is extremely effective, and hence the penguin operators are not relevant. And for direct CP evaluation, we need the interference between tree and penguin amplitude. However, for charm decays, the penguin contributions are very small. That is why the direct CP evaluation in charm decays is very, very small. So if we consider the time-dependent rate asymmetry, from there we can find out the direct CP evaluation, and instead of considering a pure single Kabeva suppressed decay mode, if we can take the difference between two decay modes, D0 going to K plus K minus and D0 going to pi plus pi minus, then from the direct CP rate asymmetry, we can find out the direct CP evaluation for these two modes, and it is found to be this one. And this measurement was done by LSCB in 2019. Then direct CP evaluation in D0 going to K minus K plus has recently been measured by LSCB experiment with 5.7 femto1 inverse dataset, which is given by this value. And if we consider the difference of direct CP asymmetry between D0 going to K plus K minus and D0 going to pi plus pi minus, then we can obtain the direct CP asymmetry in D0 going to pi plus pi minus, which is given by this value. So we can correlate the direct CP asymmetry between K plus K minus and pi plus pi minus. This one is no CP evaluation, and the black dotted line, it corresponds to the previous LSCB result, average result, and the red contour, this is 1 sigma and this is 2 sigma for the new LSCB average. So CP evaluation in D meson system is well established now. Now coming over to the anomalies in the B sector, we know that lepton Flavour universality is a key ingredient of the Standard Model. If we ignore the mass of the charged leptons, then the coupling of the gauge bosons will be universal to all the three flavors of charged leptons. However, in recent times, we have seen several discrepancies between the charged current as well as neutral current transitions in B sector. These are known as RD and RD star anomalies, which are associated with B to Cl new transition, RK and RK star anomalies, which are associated with B to SL transitions, as well as we have also seen the form factor independent observable P5 prime, and in the branching ratio of B is going to phi mu mu, and so on. So these anomalies may guide us how to probe new physics beyond the Standard Model. So quickly, I will quickly go through the recent result of RD and RD star. RD and RD star, they are defined as the ratio of branching fractions of B going to D star tau nu to B going to D star L nu. So these are the this is the world average for RD, and this is the corresponding Standard Model predictions. And for this is the value for RD star, and this is the corresponding Standard Model prediction. So we can notice that the experimental value is greater than the Standard Model prediction. Previously, the LSCB experiment measured only the RD star and RD was not measured, but recently LSCB also measured RD. So this is the latest world average of RD and RD star after including the data from LSCB, and this result is consistent with the previous result. Earlier, the disagreement was 3.3 sigma, but now it came to 3.2 sigma. So overall agreement between all the measurements. So this is the summary of the measurement of RD, RD star from various measurements. So we have seen 3 sigma deviation from standard model prediction in 3 different experiments with different tagging methods, and the measurement consistent with E mu universality, that is RD experiment. If we consider B going to D mu E, and if we take the ratio of E to mu, the universality it holds good. Similarly, Bell also measured the D star polarization and longitudinal polarization. So in these measurements, there is 1.6 sigma discrepancy. Recently, also the LSCB measured the ratio of BC going to J psi tau nu to BC going to J psi mu nu, and this value again it has deviation from the corresponding standard model result by 2 sigma. So if we consider the new physics contribution only to be going to C tau nu transition, and since these processes are mediated through tree level processes, so if we consider the new physics contribution to be 10% enhancement, then it gives us the new physics scale to be of the order of say 3 TeV. Now coming over to RK star, these are defined as the ratio of B going to K star mu mu to B going to K star EE. The standard model prediction is of the order of 1, and the experimental prediction is 3.1 sigma deviation. Previously, this measurement was done on B going to K plus mu mu to B going to K plus EE. Very recently, this measurement was done by LSCB with B going to KS mu mu to B going to KS EE, and we get similar result. Similarly, for RK star also, we are having the similar trend, and the deviation is at the level of 2 to 3 sigma. Coming over to the B going to KEE, we can see that the branching fraction for B going to KEE is almost consistent with the standard model. So it is usually considered that the new physics contribution, it affects only B going to S mu mu transition. So this is the summary of RK measurement, which is having 3.1 sigma deviation from the corresponding standard model prediction. Coming over to B going to K star mu mu, this is the decay distribution of B going to K star mu mu, and from this decay distribution we can extract the values of these parameters, and by taking suitable combination of these parameters we can construct these form factor independent variables which are independent of form factor. So they are basically almost clean observables. Now the recent LHC-B result, it gives 2.5 sigma deviation in P5 prime value in 4 to 6 sigma Q square 4 to 6 GeV square, and 2.9 sigma in 6 to 8 GeV Q square values. Similarly, Atlas results follow the same trend in P4 prime as well as P5 prime. Atlas, it gives 2.7 sigma deviation. Again, this measurement are done for B star plus going to K star plus mu mu by LSCB experiment, and again here also the same trend is followed. There is around more than 2 sigma deviation in P2 as well as P5 prime. Now, if we consider new physics contribution, since these are loop induced processes, if we consider 20% deviation from the standard model muon channel, and if we include the new physics contribution to the tree level, then the scale that we can probe is 30 TeV, and if we consider the new physics at the one loop level, we can probe the new physics scale up to 3 TeV. Another important channel is BS going to mu mu. This is again mediated through B going to S mu mu, and in the standard model it is very clean. This is loop suppressed, GCAM suppressed, helicity suppressed, and the only hadronic parameter involved in this process is the decay constant of BS meson. So combining the Atlas LSCB and CMS result, this is the result for BD going to mu mu. This is the result for BS going to mu mu, and there is 2.3 sigma deviation with the corresponding standard model result. And this is the summary of all the observables. We have more than 4 sigma deviation in muon G minus 2, then around 3 sigma, more than 3 sigma deviation in the branching fraction of B is going to 5 mu, and RK in the Q square region 1 to 1.6 GeV square and RD star. And for all other observables listed here, we are having the deviation between say 2 to 3 sigma. So if we look into these deviations, we are having discrepancies in 2 different kind of processes. One is tree level process, B going to CL nu, another is B going to SLL. This one is loop level process. Here, these are form factor independent observables, RD, RD star, RJ psi. Here, RK, RK star. These are tree level process. These are one loop process. Here, the lepton flavor universality it involves tau versus electron or muon. Here, this one is muon versus electron. So, how to address these anomalies in the B sector? As we have seen that the anomalies in B2C tau nu, it requires new physics at the TeV scale, whereas for the loop level process B going to S mu, it requires new physics around 30 TeV scale. So if we have some new physics model which will contribute to B2C mu C tau nu at the tree level and B2S mu at the loop level, then those scales will be same, and they can simultaneously explain these deviations. Now coming over to the effective field theory approach, the effective Hamiltonian describing B2C tau nu process is given by this. This is our complete set of operators. These are the operators generally we consider, that is VL, VR, and these are the combination of scalar and pseudoscalar, and then this is tensor. However, this O prime and O double prime, we can make Pierce transformation and we can write them in terms of these operators. So if we consider all the lepton flavor universality violating observable RD, RD star, and FL, and the branching fraction of BC going to tau nu, it prefers the new physics scenario, which gives new physics contribution mainly to CVL. That is the vector-like contribution to B2C tau nu transition. So OVL, it has the same Lorentz structure as the standard model. So it will give additional contribution to RD, RD star, and we can have the scenario that RD, RD star, it should greater than the standard model contribution. However, if we have the VR contribution, then it will give new physics contribution to RD as 1 plus CVR square, whereas for RD star, this is 1 minus CVR square. So we cannot explain simultaneously both RD and RD star. And similarly, if we consider new physics contribution to the scalar and pseudoscalar, it will enhance the branching fraction of BC to tau nu. Hence, we have to be more careful. Now coming over to the effective Hamiltonian describing B2SLL. This is the effective Hamiltonian which describes B2SLL. So we have basically the dominant contribution, it comes from O9, O10. So if we take the scenario that there will be one new physics contribution, and we take the scenario that O9 or C9 mu new physics is equal to C10 mu new physics, then it gives the value of C9 mu equal to minus 1.06. And if we take the combination like C9 equal to minus C10 mu, then this gives this value. So these are the corresponding results. The LSCB, if we consider all the B2S mu transitions, then the LSCB results are given by these red regions, and CMS results are yellow regions, and this one is Bell and this one is Atlas. So we can see that the best fit results are almost in agreement with the LSCB result. And if we consider only the lepton flavor universality violating observables from all experiments, then this is the corresponding values in the C9 and C10 mu parameter space. Similarly, there are also some works which consider that there will be universal new physics contribution to B to S EE as well as B to S mu mu, which are parameters like CIE equal to CI universal and CI mu equal to CI U plus this additional contribution. For this parameterization, again, we can get the new physics contribution to O9 and O10. They are related by C9 mu vector is equal to C minus C10 mu. And these values are slightly different if we consider the new physics contribution only to C9 mu and C10 mu. So leptoquark is one of the possible scenario which can give simultaneous solution to both B to C tau nu as well as B to S mu mu. So these are the leptoquarks which do not mediate list of leptoquarks which do not mediate proton decay at the tree level, and they can explain both these anomalies. So I will just give a this only one example, S1, which is a triplet under SU3C, singlet under SU2, and its charge is equal to -1/3. So since this is a singlet under SU2L, it will couple to LL and QL, or ER and UR. These are singlet and these are doublets. So we can write down the corresponding Lagrangian. Then again, we have to expand this interaction Lagrangian in terms of the mass basis. And then we can see that it will give new physics contribution to the charge current transition at the tree level, whereas it will give the new physics contribution to B to S mu mu at the loop level. It also explains muon G -2. So the issue with this model is that it allows proton decay. So one has to invoke some Z2 symmetry to prevent the proton decay. Similarly, another leptoquark model is U1 leptoquark model, and this model, it gives new physics contribution to B to C tau nu that we require, that is CB1 or CBL this way, and it will give the new physics contribution to B to SLL, like C9 new physics is equal to C minus C10 new physics. So by fixing the parameters of this coupling of leptoquark to the quark and lepton and the mass of the leptoquark, we can easily explain the observed anomalies in both the sectors. So this is the summary. That is currently we have seen anomalies in both B to C tau nu as well as the B to SLL transition. So they have huge impact on model building and also in the searches for new particles like leptoquarks and Z prime, and building a viable model which accommodates these observed B anomalies and consistent with all other measured Flavour observables is difficult. So models with leptoquarks seem to address anomalies along with some additional assumptions, but they do not provide a clear picture of any ultra UV complete model. Thank you.
Thank you, Rukmini, for excellent overview. Now, any question, comments? I don't see any hand. Cover.
So that penultimate slide, you're saying that leptoquark candidate.
Yeah.
And you need this additional discrete symmetry to prevent
it is for one specific model like S1.
Right.
But there are other leptoquark models which can simultaneously explain both these anomalies, but that requires some additional assumptions.
I see. But with that kind of leptoquark, there should be some implication for the high energy frontier in the sense that there is a direct direct limit from the CMS and Atlas.
Yes.
So how do they fit into the picture?
So these leptoquarks basically TeV scale, and they are consistent with the current measurement from CMS and Atlas.
Okay.
Okay. Any more comment, question? Okay, if not, thanks again, Rukmini, for this talk.